the next concept that is known as electric potential. So which is indicated by capital V. So meanwhile, I am going to give some instructions to you guys. That is, while you are following the class, so try to take down the notes. Okay, so try to take down the notes along with me, so that will be helpful for you to revise back. Okay, so just wait. I will recording also, that we, so that you people
recording in progress.
That will be helpful for your further. Okay, so first of all, we will see the basic definition for electric potential. So with the help of this definition, we are going to derive the basic equation for electric potential, which is given by capital V. Okay, so the generalized definition for electric potential is nothing but, if you are having a single point charge which is which is having a charge of Q, and if you are moving this point charge from one point to another point, let this point be A and let it be point B, and so here if there is a point charge of Q, and if you are doing some work to move this point charge from the point A to the point B, then we are going to call this as what? The electric potential. Okay, so the electric potential is nothing but, in simple way to tell, that is work done to move the point charge, or work done to move a single point charge from one point to another point, from one point to another point. So here we have indicated the first point as A, and the next point, the final destination point, is B. Okay, so here we know that whenever we are having a point charge of Q, and because of this point of Q, an electric field intensity, that is capital E, is going to be generated, and with this, that is already we have derived that equation by using Coulomb's law of force, that is E is equal to F by Q. So which is very much familiar for us. So E is equal to F by Q. So let it be the starting point. We are going to start with this equation, and later we are going to proceed into the derivation. Okay. So simply to say, what do you mean by electric potential? It is nothing but work done per unit charge. So voltage is equal to work done per unit charge. Okay. So first of all, we will derive the expression for the work done, and if you obtain this expression for the work done, and finally we will write that equation in the form of W by Q, and we will replace that value of W by Q with the electric potential as V. Okay, so this equation, which is nothing but E is equal to F by Q, which is already we have seen this equation in our earlier class many times, which is derived from the Coulomb's law of force, that is E is equal to F by Q. And from general derivation, from the general definition of work done, for general definition of work done is nothing but the force into displacement. Okay, so work done is given as the force into displacement. So distance is different and displacement is different. So here the distance is a scalar quantity, and the displacement, it is called as a vector quantity. These examples also we have seen while we are dealing with the scalar quantities and vector quantity. So here we have two parameters, one is force and one is displacement. Okay, so work done, if you go with work done as W, and we will go with the force as F, and the displacement as L, and the displacement as L, and we will go with the expression. Already we have got this equation, that is E is equal to F by Q. So from this, if you want to write for force, what will be the force? F is equal to what? So F is equal to E into Q. So whatever the value of F is equal to E into Q, we will replace in this form. Okay, in this expression. So therefore, work done W, or we can write or W or dW. L, or we can write it as dl. Okay, so therefore first we are writing dw is equal to f into dl. So dw is equal to f into dl. So here we are telling work done. So work done means, so definitely we will lose some energy to do that work. We will lose some energy to do that, to do any work. So losing of energy, we are going to represent with a negative sign. We are going to lose the energy. That is nothing but the loss. That loss we are going to represent with a negative sign. So therefore, dW will be equal to minus F into dl. So this negative sign is because what? So say because while moving the point charge from one point to another point, definitely we require some energy. Okay, so in order to move from point A to point B, definitely we have to do work, we have to do some work, and in order to do that work, we have to use some energy. So because of the using of that energy, we will lose it. So that loss of energy we are going to indicate with a negative sign. So therefore, dW is equal to minus F into dl. So finally, if you write that dW is equal to minus in place of F, so in place of F, we have what is the equation? F is equal to E into Q. So therefore, EQ into D into L. So now what we are going to do? We are going to integrating on both sides. Okay, so if you integrate on both sides, this expression will be what? So W is equal to integral minus EQ of dl. EQ of dl. So since Q is it is just a value, and we can treat it as a constant. Okay, so bringing that value as outside, so minus Q integral E of dl, which is the W. So if you write a W and bring this Q to the denominator, W by Q is equal to minus integral E of dl. So already I have told that what is W by Q? W by Q is nothing but what? So W by Q is, it is nothing but the voltage potential. So V is equal to W by Q, which is nothing but electric potential, which is our required equation. So therefore, we can write the value, that is W by Q, which is nothing but V is equal to minus integral E into dl. So dl is nothing but, here we are talking dl. dl is with respect to displacement. Okay, so displacement, that means it is the point charge Q, it is displacing from point A to point B. So this is called as total displacement of L. But instead of total L, you have considered a small part of L, which is nothing but dl. So if you want to get the total length, from where to where you have to integrate? You have to integrate from A to B. So therefore, V is equal to minus integral from A to B E of dl. So potential, electric potential. So it is nothing but it is also known as a potential difference. So difference between point A and point B. Okay, so that is potential at A and potential at B. Let it be, if the potential at A is VA and potential at B is VB, then the difference between these two potential is nothing but a potential difference between V and AB. So therefore, simply to write this value as, so VAB will be equal to minus integral A to B of EDL. Okay, so this is the expression for electric potential. So electric potential. So if you want to write the expression for, so electric potential between any 2 point, so that is point A and point B. So that value will be VAB is equal to minus integral A to B of EDL. dl. Okay, so try to remember this expression. So by making use of this expression, we are going to derive one of the important derivative part, that is electric potential due to a point charge. Okay, so this question they have asked many times. Okay, so by using this is just a potential between any 2 points, and now we are going to take a point charge and we are applying different cases on the point charge, and for each case we are going to derive one separate expression. So that point is important. So up to here they are going to ask for a 2 marks question. They may ask as what. So try define potential, define electric potential, or obtain the basic equation for potential between the 2 points, like that. Okay, so if they are asking that type of question, so you can write up to here. So you can write up to here. Okay, so this is nothing but what? So general definition of electric potential and general equation for electric potential between any 2 points. Now, with the above concept, what we have learned or what we have derived with the expression, that is VAV is equal to minus integral E dot dl, and with this concept we are going to derive the electric potential due to a point charge. Okay, so now we are going to see that what we are going to derive. So electric, so potential due to point charge. Okay, so this is one of the important questions. So you can have a star mark for it. So here, suppose we know that if you take a point charge, okay, so if you take a point charge and the field around that point charge will be in the form of a sphere with radius of small r. Excuse me, just please mute. Now, what we are going to have? So here we are going to have total 3 cases. So that is case 1, if the point charge is at origin. Okay, so that will be case 1. If the point charge itself is located at origin, so that we are going to consider as case 1. If not, that means if the point charge is not located at origin, so that we are going to treat it as case 2, and we are going to apply the concept of case 1 and case 2 for n number of point charges, that will be case 3. Okay, so for each case we are going to have the derivation separately, but if they ask the question for your external examination, that is obtain the electric potential due to the point charge, then you need to write all the 3 cases, that is case 1, case 2 and case 3. Okay, so now we are going to see about 3 cases. Okay, let me write it. What are the 3 cases there? So case 1, that is if the point charge is at origin. So that means whatever the point charge you are going to take, we are going to take that point charge, the location of the point charge where, so that is at origin. That is case 1. And for case 2, so if the point charge is not at origin, if the point charge is not at origin, so case finally last case, what? So we are going to apply the concept of case 1 and case 2 for what? For n number of point charges. Okay, so these are the three cases, and we are going to see them one by one. So now for case 1. Okay, so here, what is case 1? Case 1 is nothing but if the point charge is located at origin. Okay, so here we have taken one point charge and it is located at origin, and because of that point charge, okay, so a field is generated around it, and that field will be in the form of a sphere. That field is in the form of a sphere whose radius of the sphere is given as small r, whose radius of the sphere is given as small r, and the direction of that radius is given as a r bar. Okay, so now what we have to do? Masan Rao, please don't write anything on the screen. Now what we have to do? So we have to move this point charge. So let us select one location, that is this is at location A, and this is location B, and now we have to move the point charge from point A to point B. So this is nothing but moving of point charge from location point A to point B, that is the work done. So work done per displacement is nothing but work done per displacement, which is nothing but what? Voltage or electric potential. That's what we have derived earlier. Okay, so we have to find the difference, that is VA and at VB. These two differences will give the potential differences that between these 2 points, that is VA and VB. So for that, what we are going to take? So here, the location of point A, which is at a distance of RA, and the location of point B, which is at a location of RB. Okay, RB. And now we have to find the value of VAB. Okay, so this is a diagram for case 1. Here we have whatever the black dot, it is nothing but the point charge, and that is located at origin. Okay, and this blue color is nothing but the field around because of this point charge with a radius of small r, and its direction is given by AR bar, and point A and point B are the two different locations inside this field. And if you are moving the point charge from point A to the point B, and this point A is located at a distance of RA from the origin, and point B, which is located at a distance of RB from the origin, and we need to find the potential difference between VA and VB. VA and VB. Okay, so now from Coulomb's law, already we know that this expression, that is E is equal to Q divided by 4 pi epsilon naught R square into AR bar. So what is this expression? So this expression is nothing but electric potential due to a point charge. Since we are doing for the point charge, okay, since we are doing the potential for point charge, we are dealing with the point charge. So I have written the expression for electric field intensity, electric potential, electric field intensity due to a point, so not potential, so it is intensity. Electric field intensity due to point charge is given by, so E bar is equal to Q divided by 4 pi epsilon naught R square into R. And earlier we have derived one expression for voltage. So what is that potential, electric potential formula? So now, sir, are you there?
Yes, sir.
So please try to note down the numbers who are making the disturbance in the class. Okay, so later I will talk to them.
Okay, sir.
Okay. So please try to note down who are making the noise during the session. So earlier we have derived the one formula for voltage for electric potential, that is VAB, which is equal to minus integral from A to B of E dl. So now we know the value of E, that is nothing but E is equal to 2 by 4 pi epsilon naught R square into AR bar. Okay, so now if you substitute that value, that is minus integral A to B, what is E here? E is equal to Q divided by 4 pi epsilon naught R square into AR bar. And what is DL? So DL is nothing but, say, see here, distance vector. So distance vector here, it is forming in the form of a sphere. Okay. So distance vector, it is nothing but what? Distance in the form of vector, it is a displacement. So here in the formula, it is a dl bar, and here it is a sphere. In sphere, we have expressed with respect to radius. Okay, so that radius is nothing but r. Of complete r, a small differentiable element of what? Dr. This dr is along AR bar. So what will be the value of DL bar? So DL bar is equal to dr into AR bar. Okay, so try to understand this concept. Distance vector is nothing but the displacement. So displacement is nothing but the dl. Here we are taking a single point charge which is forming a spherical coordinate system. For spherical coordinate system, the distance vector is nothing but the radius. And instead of complete radius, we are considering a small part of it, that is dr. And this dr is along which one? That is along with AR bar. So therefore, dr along AR bar, that is nothing but dr into AR bar, which is nothing but the displacement for sphere. So therefore, whatever the value of dl is here, so we have to replace with dr AR bar. Okay, so dr AR bar. So therefore, that value will be the minus integral from A to B Q divided by 4 pi epsilon naught R square into AR bar. What is dl? So dl bar, that is nothing but dr AR bar. So either you can directly represent in the form of a vector form, or you can write it in the form of a scalar form. So if both doesn't matter. So here we know that dot product between any two similar unit vectors is always equal to 1. So therefore here AR bar dot AR bar, the value will become 1. So final that value, that is equal to minus integral A to B. So Q divided by 4 pi epsilon naught R square with respect to dr. So if you do the integration, that value, that is equal to minus Q divided by, so 4 pi epsilon naught integral A to B 1 by R square dr. So what is the difference, and what is the integral of 1 by R square? That is equal to minus 1 by R. So minus of minus, we will get plus. So therefore Q divided by 4 pi epsilon naught 1 by R, upper limit is B, lower limit is A. So this is equal to what? So Q divided by 4 pi epsilon naught, upper limit, that is B minus 1 by A. So see here, in place of R, you should not write it as 1 by R, 1 by B minus 1 by A. This, if you write it, so this will become wrong. So why means, so what is the reason means why here whatever the what is A and what is B, here A is nothing but we have given the name for this point as A, and we have given the name for this point as B. But A and B are not the values. They are just a name. Okay, they are just the name. This point A is with respect, so here you are doing integration for R. So you have to substitute the value of R. So value of R at A. So what is the value of R at A? That is RA. And what is the value of R at B? That value is RB. So that is the main point where you have to understand. So here, if you go with the 1 by RA, 1 by RB minus 1 by RA means, so the A and B are not the values. Okay, so but here the limits are values, but here A and B, actually A and B are not values, they are just the names. So names we cannot substitute, we have to substitute the value. So with respect to A, it is at a distance of RA, and the point B, it is at a distance of RB. So upper limit in place of is RB, in place of A, we have to write it as RA. Okay, so RB minus RA. So therefore, finally, what is the expression? So electric potential, so due to point charge, which is located at origin. So that is given as, so VAB, that is equal to Q divided by 4 pi epsilon naught 1 by RB minus 1 by RA. Okay, 1 by B minus 1 by RA. So if you extend this, so this is equal to Q divided by 4 pi epsilon naught RB minus Q divided by 4 pi epsilon naught RA. So let it be, this is VB and this is VA. So VAB is equal to VB minus VA, where VB is equal to what? So Q divided by 4 pi epsilon naught into RB, and VA is equal to Q divided by 4 pi epsilon naught into RA. Okay, so this is the expression for case 1. Okay, just wait, I will check the time, running time. Okay, 8 more minutes. So this is the so in this class we have seen what do you mean by electric. We have seen the basic definition of we have seen about electric potential, and we have derived the final we have seen the basic definition of electric potential with respect to work done. So simply to say, what do you mean by potential difference? That is nothing but work done per unit charge. Work done to move the unit charge from one point to another point. So, and finally, by using the Coulomb's law of force expression and with the basic definition, so we have finally obtained. So W by Q is equal to integral E dot dl, which is equal to V is equal to minus of. I have already given this reason for minus. Minus is because of what? So if you are going to do some work, you are going to lose some energy, and that loss of energy we are going to indicate with a negative sign. And finally, we have got this expression, that is VAB is equal to, so VAB is equal to minus integral A to B E dot dl. Okay, so electric potential due to next we are having the next derivation, that is electric potential due to point charge. And here we have total 3 cases: case 1, case 2, and case 3. and in this class we have we have obtained the expression for electric potential due to the point charge if that point charge is located at the origin. Okay, so and for that we have gone with first of all we have written the expression for electric field intensity due to point charge from Coulomb's law, that is E is equal to Q by 4 pi epsilon naught R square into E R bar. And from the earlier derivation of electric potential, we have taken this E VAB is equal to, so VAB is equal to minus integral A to B E of dl. And whatever the E we have substituted here and we have proceeded. And this is the important the thing where we have replaced the value of dl with the dr ER bar, and finally we have proceeded with the derivation. And final thing is, in place of R, we should not substitute as A and B because these are just the names of the locations. Whatever the locations we have selected, we have named them with respect to the locations. So therefore, we should not substitute the location name, but you have to substitute the value of the location as RA and RB. So therefore, we have given the expression as Q VAB is equal to Q by 4 pi epsilon naught 1 by RB minus 1 by RA. And finally, we have got the expression that is VAB is equal to VB minus VA. VB minus VA. So this is about case 1. And by using the above case 1, okay, by using the above case 1, so we are going to see for case 2, that is nothing but, so if the point charge is not located at origin. Okay, so that thing we are going to see in the next class. Meanwhile, I will go for the attendance.
Recording stopped.
Mastan Rao 244 no ade paniga inka alage unnav, so you have not at all need yourself. So sorry guys, I will not give you attendance. Work na petesi వెళ్ళిపోవడానికా? So have you anyone, I mean, Naushad, have you taken the attendance for early anyone who are?
Sir, screenshot I have taken, sir.
So can you send it me through WhatsApp? All the 70
Sure,
participants.
sure, sir. I'll send, sir.
All the 70 participants, please send it to me.
Okay.
Okay. Screen visibility బానే ఉందా మీ అందరికి?
Yes, sir.
So if possible, I will have this recorded video I will share it to you. Okay, so that you can verify it again and you can write down the notes, so that will be helpful for you to take the notes. So you people may not be possible to take the notes while listening to the class. So okay then, that's all for today. And Roshan and Sangade. Roshan, any doubt? You have raised a hand. One more. 225. So okay then, have a nice day, and we will continue with the case 2 and case 3 in the next tomorrow session, so that we can by finishing off. So we are having 2 more derivations. that is electric dipole and torque due to dipole. So those two derivations are also very much important with respect to electric potential. So any of the essay type question you can expect in your external examination, that is the today's class, that is electric potential due to point charge, and also tomorrow's session, that is electric dipole as well as torque due to dipole. Okay, so that's things we will see in the next session. So thank you all for today.